I am going to turn that back off. Okay, reviewing for the exam. We've just finished talking about astronomy. We learned about constellations a little bit. We learned about the celestial sphere. We learned about the planets. It's primarily what we learned in astronomy. Now we're going to go back and just look at what we've learned throughout the semester. Because the exam is, as with most classes, we hope that you leave the class with more knowledge than you came. And so it's going to cover the entire semester to check to make sure of that. And so the stuff we started with is probably really fuzzy in your minds. That's why I'm starting there. So we started with physics because it's the fundamental science. But even before that, we had the scientific method. And you know now 2 questions are going to be on this exam. One question will be listing the planets in order from the sun outward. So
not including Pluto?
No, not Pluto. So remember, as Lindsay gave us her mnemonic, which is very similar to the one that I gave you. Lindsay's was my very educated mother just served us.
It was pizza, but Pluto's.
Yeah, it originally what I learned was my very first mother just served us 9 pizzas. And so instead of having the 9 pizzas, my students decided nachos, and Bryson thought that was a good plan. So that'd be Mercury. My has a Y at the end for Mercury. Very earnest. Mother, the other M is Mars. Jupiter, Saturn, Uranus, Neptune. Okay, but the other question that you have is the one on the scientific method. Why is the scientific method so important that we had it on both the first exam and on the final exam?
Because it is the fundamentals of science itself.
Yeah, it's what science is all about. If knowledge is derived through this method, we call it scientific. And so the scientific method, and you find different variations on it. Our textbook has a different variation on it than what I have here. But this is what I will be grading on. So the first step is observing something interesting. It's an often overlooked, but it's an important step in the scientific process. If you're not thinking about things and observing and curious, then you're not going to follow the method. Then you create a hypothesis that has these 3 things, right? You can't just create a hypothesis. Your hypothesis needs to explain why the observation occurred. Why did it happen? So, something of the simplest form. We say the simplest form. Back in the day of Aristotle, they had a different answer, so it couldn't be that simple. If I take this ball and drop it, we observe it falls. Very simple observation. And then the explanation of why, Aristotle said, well, it was because the natural position for the ball is on the ground. And so it's doing what's natural. Nowadays, we say it's because there is a force due to gravity. Based on scientific ideas, needs to explain what's happened and make testable predictions. So testable prediction, for Aristotle's idea, well, if I take something that has less air and less earth and more air, this natural position is not as much on the ground, so it should fall slower. Right? That would be a prediction that hypothesis would have made. Whereas using the one we accept today, you'd have a different set of predictions. So it has to explain why the observation occurred, be based on scientific ideas, and make testable predictions. Then you do an actual experiment that tests a prediction. It doesn't go back and test and make sure what you observed is really what happened. We're assuming that what you observed is really what happened, that you didn't say, oh, he let go and the ball fell, but actually he let go and the ball stayed stationary. Right? We're assuming the observation is correct. So you're not redoing the observation, but you're testing a prediction made by your hypothesis. And then finally, if the hypothesis prediction is correct, then you go back and you test differently. If the hypothesis prediction is incorrect, then you go back and you change the hypothesis. So you're going to have to regurgitate this list. So you have the 2 options here in step 4, the 3 pieces in step 2. And then I'm going to give you an observation, and you're going to have to apply it to the observation. So you're going to, if I were to give you the observation that a drop ball falls, you'd say my hypothesis is that it falls because of gravity. Or you can have other things, but it needs to be based on scientific ideas.
So I can say, I believe the ball falls because yellow things are on the ground. And then if I back it up, it's still correct.
I'm not sure that yellow things on the ground is a scientific thing.
But what if I say because
There's no causality.
because whenever I see bananas, they're not in the air.
Yeah.
So therefore, a tennis ball
What if
doesn't
you
want
have
to
it?
be.
I would
A
usually
yellow
better
hot
like
air balloon.
dandelions because they're on the ground.
Yeah, you can say dandelions.
But hot air balloons are sometimes yellow when they're in the air. So
But it needs to be something that you can back. This is a scientific idea. It's not just a random thought.
I agree with that.
And then, of course, you need to actually come up with, this is the experiment I would do.
So are you not giving us a thing already, like you did on the first test?
What does the thing already mean?
Like when you gave us the thing we had to,
come up with the.
yeah, what is it like?
It's like.
Well, I give you the
say-
observation
it's-
again.
Yeah, are you gonna give us that?
Yeah.
Okay.
Yeah, so your hypothesis will have to explain why the observation occurred. And then your test has to be a test of a prediction the hypothesis made. And then for the last step, you say, if I get this outcome, then it matches my prediction, and I go back and retest differently. If I get this outcome, then it doesn't match my prediction, I have to go back and change the hypothesis. So you need to specify what the actual outcomes are that would cause those two. Okay, so now doing actual physics. One of the first things we learned about was about forces. We had to learn about motion, about speed, velocity. What's the difference in speed and velocity?
Velocity has direction.
Velocity has direction, speed doesn't. And acceleration, what's the difference between speed and acceleration?
Acceleration doesn't have you can accelerate even if you're turning right, but speed is a straight line.
Yeah, acceleration.
Your first statement was correct. Acceleration is anything that is changing the velocity. So if you're speeding up, that's changing velocity. If you're changing direction, that's changing velocity. If you're slowing down, that's changing velocity. So all of those are accelerations.
So if you're going forward but you're slowing down, you're accelerating backwards.
Correct.
That's weird.
So some people call that deceleration, which is an accurate term. I try to avoid using deceleration because then you add more confusion, because deceleration is an acceleration in the direction opposite velocity. So it's still an acceleration. We also learned about then Newton's laws. And Newton's first law, the law of inertia. It's a fundamental understanding we have. It's not something that we have a reason for other than it always occurs, and so we believe it's fundamental to nature. And that first law is something stays in constant motion unless a force causes it to change. Prior to Newton's law, people like Aristotle believed that it was just natural for things to be at rest. And so something slowing down was just natural because it's natural for it to be at rest. And if you make it move, that was a violence. That was making it do what it's not supposed to do. Newton's second law was the super important one that said the sum of the forces, otherwise known as the net force, is equal to the mass times acceleration. Now I'm putting arrows above the F's and the A. What do those arrows mean?
Direction.
They mean that it has direction, so it's a vector. So the sum of the force vectors is equal to the mass times the acceleration vector. And so we use that many times, and you should be able to use that. If you're given a certain object and a certain acceleration, you should be able to calculate what the net force is. If you're given an object and it has two forces acting on it, you're only going to have to worry about them acting in the same direction, so either like this or like this. then you need to be able to calculate what the net force is. So let's just look at that real quick. Let's suppose that I have a box here, and if the box is sitting on the ground, what forces would you typically say have to be there?
Gravity, normal force.
Okay, I was looking for the two Bryson said. We will get to what you said though. So we normally would have gravity, which by definition is down and has a value of mg. And then we would have normal, which is the direction coming out of the surface. Remember, normal isn't necessarily up. For instance, if I push on the wall, the normal force acting on my hand from the wall is out of the surface, so it's horizontal. So we always are going to have those if it's sitting on a surface and if it has mass in the Earth's gravitational field. Then if it's moving or if there's another force, so let's say that I have now an additional force of somebody pushing on it. So I have a force pushing like this. If there is friction, what direction is the friction force going to point? So we have the force of friction. And let's just put numbers to these. Let's say that this is 10 newtons, and this is equal to 1 newton. In the direction, what's the net force? No, in the horizontal direction, what is the net force?
Oh.
It's going to be 9, because you have 10 in one direction, 1 in the other. So you'd have the net force. I'm changing to black. So you'd have the force net in the horizontal direction. We generally call the horizontal direction x, vertical direction y, is 10 newtons minus 1 newton equals 9 newtons. And if this has a mass of 2 kilograms, how do I find the acceleration then? If mass is 2 kilograms, I know you can't read that. Also, you can't read that, but that's not so much my fault. It's supposed to be erasing. You can tell because of the outline. There we go.
9 divided by 2.
Okay, we test this law right here. Force net equals ma. Solve it for A.
Equals F over N.
So that would be equal to 9 newtons over 2 kilograms equals 4.5. And then what are the units going to be?
Kilograms per second squared.
Well, a newton is a kilogram meter per second squared.
So then it would just be meters per second.
And so if we cancel the kilograms, that's meters per second squared. So that was our unit for acceleration, meters per second squared. Now that's the acceleration in the x direction. What is going on in the y direction here? Assume that my blue line is a perfect horizontal line, by the way. Yeah. It's zero acceleration in the vertical direction because the normal force is whatever is necessary to keep it from breaking the surface. So if you're pushing down with the force mg, the normal force is just going to be the same magnitude and up. So if I stand here, I have a downward force that's equal to my weight acting on the ground, and the ground has equal upward force acting on me. How is it then that I'm able to jump?
Because when you apply a normal force that's greater than your weight, you go up.
Okay, when I push down, when I go like that, my feet are pressing on the ground harder than just my weight then. And then the ground is pressing back with exactly the same force, but that makes the net force on me upward because the ground is pressing harder than gravity is pressing down on me. Okay, so that's Newton's second law. Newton's third law. Newton's third law is best described like this. If I punch this, it's going to hit me with exactly the same force in the opposite direction. If I punch this hard, what's going to happen?
You're going to hurt your hands.
I'm going to hurt my hand, break my knuckles. Why? Okay, because this thing is, I'm going to go with just hard. I'm holding it. It also is density. If I threw it up in the air and punched it, I'd still break the knuckles, and then it's because it's dense. it's going to have the same force on the metals it has on my knuckles, but surprisingly enough, my knuckles are weaker than the metal. And so they're going to break, the metal's not going to. If you know somebody who can break iron with their fist, don't ever make them angry. So we had Newton's 3 laws that are really important. You're certainly going to have at least a question on each one of those. Equilibrium means equal forces. If something's in equilibrium, it has equal forces pushing on it, so the net force is 0. It can be moving. It's not accelerating.
Oh, okay.
It can be moving at a constant velocity. Almost all of our equilibrium problems are not, and so people get that idea. I've gone through all of these. Momentum and energy. Momentum is mass times velocity. When something has momentum, it's going to be hard to stop it. More momentum it has, the harder it's going to be to stop. And so remember our examples. I push somebody. If I push on them, they're going to push on me. We have equal and opposite forces according to Newton's 3rd law. And if there's no external forces, that's going to, if I push, let's imagine that Bryson's up here and I push him. Well, Bryson is technically pushing me. His chest is pushing my hands or whatever. And so he goes one direction, I'm going to go the other direction, unless we have friction. So when we talk about momentum, momentum will be conserved if there's no external forces. Now, something like a car crash, or as we did in lab, we did the collisions between our carts. We said the momentum was still conserved because the collisions occurred in such a short time that there wasn't time for there to be a significant change in momentum. So momentum is conserved based on Newton's 2nd law. Here's another way of writing Newton's 2nd law. The net force is equal change in momentum over change in time. So if, remember, force net is the same as the sum of the forces, then delta P equals 0 if F net equals 0 or delta T equals 0. So we have our condition where momentum is conserved. Then we go to work and energy. Work. If I throw this ball, okay, Bryce, I'm going to throw it to you. Hopefully not hitting anything important. If I throw that ball, I did work on the ball. How do you know I did work on the ball? Because it moved. Work is force times the distance it moves parallel to that force. And so I put a force on it, moved that direction, I did work. That work caused it to change its kinetic energy. Energy is the ability to do work. Kinetic energy is the ability to do work because it's moving. And so when Bryson caught the ball, a little offline, but he reached up and caught it, it pushed on him, right? Now the ball wasn't very heavy, so it didn't push very hard because it didn't have much momentum. But it did work on Bryson when he caught it because he took away that kinetic energy. So we have equations: work is equal to force times the distance parallel to the force, and kinetic energy was 1/2 m. What does m stand for? Mass. Just want to make sure. What are the units of mass? Kilograms. Not grams, but kilograms is the standard unit. And then v squared. What does v stand for? Okay, if it has an arrow over it, stands for velocity. Without the arrow over it, it stands for speed. Capital V we use for volume. Then we also have potential energy. Potential energy is energy something has because of its position. And so taking that ball, if you raise the ball and you drop it, it's going to have a higher speed when it hits the ground than if you start lower, which means it's going to have more potential energy when you have it higher. And it turns out because work is force times distance and the force due to gravity is mg, the potential energy is mg times the height it's at. So if you let the ball go, it's going to convert potential energy into kinetic energy. By the time it hits the ground, potential energy is dropped to zero. Its kinetic energy is equal to the potential to start with. Remember the bowling ball demonstration I did? It started up here with all potential energy. I let go and it converted that potential energy into kinetic energy and then back into potential energy. And so if everything was perfect, you know what, life is not always perfect. If everything was perfect, that ball would have swung up to exactly the same height because it has the same total energy. But it's not perfect, there's air. And that air is going to take away energy from the ball, and thus it doesn't swing up quite as high because it lost some energy because of making the air move. Projectiles. If I throw the ball up, simple question, why does it come back down? Gravity. So gravity is putting a force on it of mg, but we know that net force is mass times acceleration. So right away, saying those two equal to each other, mg equals ma, you find that g is the acceleration. And so anytime that ball is in the air, anytime the ball is in the air, the acceleration on it, if we ignore air, which we will in every case, if we ignore air, the acceleration is constant throughout its flight. So when it's going up, what is the acceleration?
Down.
It's downward, and what's its value? You can say three different things and I'd be happy. How big is the acceleration?
Isn't it based on its mass?
It's not based on the mass because remember we had ma equals mg. 10 was one of the acceptable answers. 9.8 was another one of the acceptable answers. 9.8 meters per second squared. Our textbook says 10 is close enough to 9.8 and it uses 10 meters per second squared for the acceleration. So while it's going up, it has a downward acceleration of 9.8 meters per second squared. When it's coming down, what's its acceleration? 9.8 meters per second squared. Now, following the words that Bryson used earlier, when it's going up, what direction is the velocity? When it's going up, its velocity is up. What direction was the acceleration? Down. And so if the acceleration is opposite to the velocity, what did Bryson call that? Deceleration. Right? I never use that term generally because I don't want to confuse. Because the acceleration is still 9.8 down, it's just opposite v. When it's coming down to the same direction, then it's just acceleration. What about when it's at the peak? Nice job. Wait, okay, let's read about the ball. Distraction. What is the acceleration when it's at the peak of its arc?
Down.
Not zero, but that's the misconception that we want to make sure that we address. Its velocity is zero at that instant, but its acceleration is the force of gravity, mg, divided by its mass, m. mg over m is g. So at the top, it still has an acceleration of 9.8 meters per second squared down. It stopped momentarily. If the acceleration was zero, what would it do?
It would just stay there.
Right, the velocity would stay at zero if the acceleration was zero at the top. All right, got those.
What is escape velocity? I don't know what you're talking about.
What is escape velocity? Escape velocity is how fast something has to have to leave. We actually,
How fast is that?
I forgot to cross these out when I was crossing stuff out. Don't worry about those.
Oh my goodness.
So what about the circular one? Circle one?
About the orbital stuff, yeah.
After we already write it down.
I just.
Which thing?
That's what
Oh well.
About orbital things.
Oh well.
Don't worry about the last three or the first three.
The stuff that's in the box.
Can you cross it out? Description. Yeah. Because the box makes it look like
It's important? Okay, yeah, I understand. I was going to change, but I'll wait for her to take a picture.
See, us teachers.
All right, then we got to fluids. We spent a fair amount of time learning about fluids. So you need to know what density is. That's the mass per unit volume. So iron, we consider dense until we get to nuclear physics. or well, until we got to geology, we learned that stuff on Earth is fairly low density for the most part. Water has a density of 1 gram per centimeter cubed. That's something we're very familiar with. Air is about 1/800th the density of water. It's far less dense. So make sure you know what density is, the mass per unit volume. Pressure is the force per unit area. So if I place this on my hand, it has a fairly low force, and thus the force per unit area, its area here is like, a little bit more than a square inch. Force per unit area is pretty small because it's a small force on, let's say, 1.5 square inches. This one here is much heavier. It's a much bigger force. If I put it in my hand, even though this is like 4 times the area because the weight is more like 500 times, that means the pressure is much bigger. The force divided by the area is much bigger. Now, if I take this on my hand and compare it to putting it on my finger, what's the pressure difference like if I have it on my finger instead of on my hand?
Higher.
It's higher because the area it was on was smaller. This plays out in important things like air pressure. Air pressure is due to the weight of all the air above us. And that air pressure is pushing in on us with pounds per square inch. So if you take just my hand, and you say the top of my hand is about 4 inches by 8 inches, that's 32 inches. At 15 pounds per or 15, that's like, well, is it 4 by 8? Yeah, 32 square inches. Let's just go to 30 because that's easy. So if it's 30 square inches, and if we have 15 pounds per square inch of force, then I have 450 pounds of force pushing down on the top of my hand just due to air pressure alone. That's a really big force, right? But I'm able to hold my hand out here, not because I'm super strong. We can all hold our hands out here. How can I hold my hand out here if I have 450 pounds pushing down the top?
Because you have to push on the bottom.
Because the air pressure is the same on the bottom and it's pushing up because pressure always makes a force into the surface. And so we don't even really notice this, but it's there. Now, if you go in water, the pressure increases with depth. The equation for the increase in pressure, change in pressure, is equal to the density of the fluid times G times the depth. So for air, since air is like 1/800th of the density of water, the change in pressure when you go up an inch is minimal. In water, well, it's small, but not as small. And if you take like my height is, like 1.9 meters. You take the density of water, which is 10 to the 3rd kilograms per meter cubed for water. Multiply that by G, which we'll use the 10 meters per second squared. Multiply by my rough height of 2 meters. And we have 2 times 10 to the 4th kilograms times meters over meters. Well, it's newtons per meter squared if you do it all together. 2 times 10 to the 4th newtons per meter squared. That's a pretty big pressure difference. 1 atmosphere is basically 1 times 10 to the 5th. So that's about 2/10 of an atmosphere difference between the pressure of water at my head and at my foot if I'm completely submerged.
What does suction cup work in space?
No. Okay, so we have a good question there that's relevant to the topic. Suction cups, remember I brought in that suction cup that was just a piece of rubber with a handle on it. It works because you have low pressure underneath the suction cup between it and whatever you attach it to, but you have atmospheric pressure on the outside.
It's all the air pressure pushing down, keeping it from.
Right, you have the air pressure pushing down and nothing pushing up, so the surfaces are being pressed together by the air pressure outside.
So it has nothing to do with the air expanding on the inside, and that's what's tough.
The air expanding inside lowers the pressure inside. So yes, it does have to do with that because that's how the pressure
But that's
goes down.
not what you're feeling when you're holding that. You're feeling
when you're pulling up, you're basically just feeling the weight of whatever you're lifting.
Yeah. And that's due to because the atmospheric pressure of 15 pounds per square inch is pushing down on the suction cup. And none of that is able to
Well,
get into
it's pushing the suction cup and the thing you have together. Right, so that the atmospheric pressure is not directly affecting you, it's pushing those things together. So when you lift up, you have the weight of both of those is what you're lifting.
So at a lower or at a higher altitude, would it therefore be easier to release the suction?
Yes, because the external pressure is smaller, you would have less force pushing them together. Okay, Archimedes' principle. Archimedes' principle, remember we had the fun lab, I think it was fun, where we studied floating and sinking. And Archimedes' principle said that the buoyant force, the net force pushing up on something that's in water is equal to the weight of the displaced water. And in general then, that allows us to calculate what the buoyant force is. If something displaces water, we just measure the volume it displaced, calculate what the weight of that water is, and that's what the buoyant force is. But that buoyant force results from the difference in pressure at the top and the bottom. And finally, Bernoulli's principle. Explain the phenomenon. Do you remember the term Bernoulli's principle? Vaguely. Remember my blow dryer?
Oh, yeah.
That was to illustrate Bernoulli's principle. The faster the fluid is flowing, the lower the pressure. Bernoulli's principle says that the difference in pressure between like atmospheric pressure and moving air is equal to 1/2 the density of the air times the speed that it's flowing squared. So the faster the air is moving, the lower the pressure, which has some important ramifications. Things like that's how airplanes fly. Airplanes, the wing cuts through the air and the top of the wing is curved, so the air has to go faster over the top than it's going underneath. And since the air is going faster over the top, the pressure on the top is smaller, and that's what holds an airplane in the air. Same thing as why sailboats work. Also why houses lose their roofs in tornadoes. Thermodynamics. Thermodynamics, studying heats and temperatures. Make sure you know the difference between heat and temperature. Heat is a transfer of energy. Just like work was a transfer of energy. Work, force times distance, that's a mechanical. Temperature is a measurement proportional to the average kinetic energy. So if temperature goes up, the average kinetic energy, remember we saw kinetic energy is 1/2 mv squared, is going to go up, so the molecules are moving faster. So when air is hot, the molecules are moving faster. It starts getting really convoluted when you think about how that affects you. If the air is hot, I feel on my skin something different. Well, what am I really feeling? Molecules are hitting me harder. And those molecules hitting me harder are transferring energy to me, or not taking away as much energy from me as they're transferring to me. And that's why I feel that temperature. We had 4 laws of thermodynamics. The 0th law.
Why does it say 3 laws then?
That must be, the reason it says 3 is because that number there is 3. That's a mistake. You are good at that. That is good at reading carefully. So there are 4 laws. The 0th law is one that seems so obvious nobody thought was necessary until later. And that's if this thing's the same temperature as that thing, and that thing's the same temperature as another, then the first and the last are the same temperature. The first law then, energy cannot be created or destroyed. That's really important in physics. It also leads to some confusion in astronomy. The second law, heat naturally flows from hotter materials to colder materials. So heat, if I have a hot stove and I put my hand on it, because my hand is not as hot as the stove, heat flows into my hand and I feel it. Or if I take my hand and I put it on ice, what direction is heat going to flow? To the ice, because it's lower temperature. Heat will just spontaneously flow if you have 2 things in thermal contact, 2 things where heat can pass, and they're different temperatures. We call it thermal equilibrium if they're in thermal contact and there is no heat flowing, but that means they have to be at the same temperature to be in thermal equilibrium, which actually goes back to part of the definition for the zeroth law. And then our third law, nothing can reach absolute zero. I already talked about that. When you add heat to something, it's typically going to make the molecules, if you add energy, what happens to the molecules typically? They go faster. If they go faster, what does that mean in terms of temperature? Increases. So typically, if you add heat, which has a symbol of Q, remember, this triangle is the Greek capital delta, and it means change, and it means final minus initial. So the heat results in a change in temperature, almost always. When does it not have a change in temperature? If you're melting or freezing or boiling or evaporating. Then the energy is going into, if you're adding heat, it's going into causing the molecules to break free of each other instead of making them go faster.
What are the M and the C?
M is the mass, and C is what we call the specific heat. That's something that it depends on what the material is, so it's just a proportionality depending on the material. And that is important. The specific heat for water is large. Large compared to most other materials, which means that water has a significant effect on our temperatures. If you're around a lot of water, like if you live next to the ocean, that's a lot of water. If you have a lot of heating that's coming from, like, let's say, the sun or hot air, it's not going to cause the ocean temperature to change very much because it has a large specific heat. So that means the air temperature is not really going to get much hotter when you receive a lot of heat if you're next to a big body of water. If you're not next to a big body of water, you'll have much more dramatic changes. And that also applies to the air. So we can consider what we've just done in astronomy. If you're on Mercury, you have no atmosphere, you have no liquid water. The rock has a much lower specific heat, which means you put heat in, it gets much hotter than it would if it was water. You allow heat to leave, it gets much cooler. So we have that question about why are the temperatures so radically different on Mercury? And one of the big answers was because it doesn't have an atmosphere. A smaller answer that we didn't use was because it doesn't have liquid water, or water, I should say. It doesn't even have to be liquid. Because water has a large specific heat, whether it's liquid, solid, or gas phase. Yep, answer. Actually, yes, as you say, answered all of those. I start changing, and then, except for thermal expansion. Thermal expansion, once again, relates to the motion of molecules. If you heat them up, they move faster. If they move faster, they bounce off each other and they expand. So almost everything expands when you heat it up. There's one notable exception. Water below 4 degrees Celsius, if you heat it up, it's going to contract. That's a unique, weird thing about water, but it's really important because that means that frozen ice is less dense than liquid water. If it's less dense, what happens when you put ice together with water? Less dense things, what do in more dense things? They float. So ice floats, you have ice that stays on the tops of your lakes, and then that forms a barrier to keep the lakes from cooling. It blocks the heat flow from the water to the air, and so your lakes don't freeze solid. If the ice was more dense, it would sink, and you would actually have your lakes generally freezing solid in the winter. So thermal expansion, you heat something up, it expands. We're almost out of physics. Heat transfer, I think we have this, and the electricity is all we have left. There are 3 mechanisms for heat. Direct contact, which is called conduction. So when I touch the stove, that's an example of direct contact or conduction. Convection, if I put my hand like an inch above the stove, it's still getting hot, and that's primarily because of the hot air rising. If I put my hand an inch to the side of the burn, it doesn't get nearly as hot because the hot air is not rising to hit it. So convection is the heat being transferred by an intermediary. And then we have the third one, radiation. That's waves transferring energy. If I put my hand to the side of the burner where I'm not getting convection, the heating will be because of the radiation. So you have those three types of heating. What type of heating are we receiving from the sun?
Radiation.
That's right, we're receiving radiative heating from the sun. Because there is no direct contact, I'm not touching the sun. There's no fluid flowing between us and the sun to any significant effect. There are protons and whatnot flying from the sun to us, but it's a very small amount. The greenhouse effect. In today's world, that's a very important thing to have some idea about, I think. So the greenhouse effect, in its short form, we have an atmosphere that allows visible light, that's radiation, to come through it. So heating from the sun comes in easily. But the Earth is a much lower temperature. Because it's a lower temperature, the radiation we give off is in the infrared spectrum. And the atmosphere blocks infrared radiation. So the radiation from the Earth going outward gets absorbed in the atmosphere and generally is staying in. So it's a lot easier for heat to come in than for heat to leave. The result is the temperature of the Earth rises until you reach a balance. And so the greenhouse effect is temperature. As we said, the greenhouse effect is vital. Without the greenhouse effect, there's no life because we're frozen. But the greenhouse effect can also be too much, such as we observed with mercury, where the temperature is so hot that nothing could survive. So it needs to be just right. And the concern in today's world is that the greenhouse effect is increasing because of pollution. Yes?
I thought Mercury is the one that has no atmosphere.
The what? Did I say Mercury instead of Venus?
Yeah.
I meant Venus.
Okay. I was
You are
so
correct.
confused.
Yes, and I do not intend to confuse. Okay. Water. Well, we talked about why water is unique because it expands when you heat it if you're under 4 degrees Celsius. And, okay, what was the other one? And it has a large specific heat. And both of those things are pretty vital to us, especially, if you live on the coast, it gives you nicer temperatures, not as big a fluctuation. Finally, electricity. We didn't have very much coverage of electricity until we got to chemistry. And so you need to know what electric charge is. Electric charge, well, we have electrons that have a charge of minus 1.602 times 10 to the minus 19. Put the minus in the wrong place. Coulombs. And we have protons that have a charge of plus 1.602 times 10 to the minus 19 coulombs. Now, you do not have to have those numbers memorized.
Oh, we don't.
No.
So just negative charge.
Yeah. So you have the negative charge electrons, the positive charge protons, and that's basically what we have for our charges. And we have rules that say electrons and protons have opposites. That's an O. I wrote O a second time because my first one didn't look good. Opposites attract. Likes repel.
Is Columbus spelled right?
Coulomb, not Columbus.
I know. I thought I said Colombo.
Oh, well, it's Coulomb. I think that's right.
Is that likes or likes?
Likes, L-I-K-E-S. Like things that are alike. So that means that a positive charge attracts a negative charge, but a positive charge repels another positive charge, or negative charge repels another negative charge.
Is that lab we did with the magnets?
Balloons.
Or is it the balloons?
Yes, with the balloons, that's where we saw that. And we have a law, Coulomb's law, that says the force is equal to K Q1 Q2 over the separation squared. Now that's very similar to
G or Q?
G. Well, it depends on which equation you're looking at.
Blue is Q's.
The top one is Q's, the lower one is a capital G. The lower equation is the law of universal gravitation. that says that the gravitational force is proportional to mass 1 times mass 2 divided by the separation squared. The other one is the Coulomb's law, the force between charges, that says that the force is proportional to charge 1 times charge 2 divided by the separation squared. Those forms are the same. In both cases, if they get farther apart, the force gets less. So once again, turning to what we just finished with gravitation and planets, we have our whole solar nebula theory that starts with you have a cloud of gas, a shock wave makes things closer together, but when they're close together, the force of gravity is stronger and makes them collapse. With electric charge, if you have something like in the sun where we have a plasma, you have, let's just take the electrons in the plasma. Those electrons all have a negative charge, so they're all repelling each other. And so the negative force is keeping the electrons from collapsing. And it really makes a difference when we get to white dwarfs, but we didn't get to white dwarfs. Now we get to chemistry. Huzzah, yay, we're done with physics.
Skip 9 and 10.
Yes.
Actually,
We skipped them. So with chemistry, we are talking about what's going on with atoms. And so we have to have some understanding of the periodic table. So we spent a lot of time actually learning about the periodic table, learning about the periods going down and the groups going across. And you need to be able to identify the group in column 1 is called the alkali metals. The group in column 2, the alkali earth metals. The group in column 17 is the halogens. Now what's special about column 17? You have one less than a complete shell. What's important about column 1? You have one more than a complete shell. And so column 1, they have a low electron, electronegativity. I was going to say electron affinity, but electronegativity is the same thing. And the numbers we have are electronegativity. So the things in column 1, the alkali metals, they're happy to give up an electron, have a low electronegativity. The things in the halogens, they really want an electron to have a high electronegativity. And so those things will easily form a bond where the thing that's the alkali metal gives up an electron. The thing that's a halogen says, gimme, gimme, it grabs the electron, but then you have something that's positive and something that's negative. And Coulomb's law said that opposites attract, and so they're held together because of those opposite charges. And so that's how ionic bond works. The last column there, the noble gases or inert gases, because they have completed shells. And then the things that are under the elements there, those are transition metals. Okay, so we have to stop here and we'll continue reviewing on Friday. Remember, no lab tomorrow.